You have heard the last few days some fundamentals about fracture mechanics, and you have seen that fracture mechanics is a certain type of continuum mechanics. Yes. And continuum mechanics has, in principle, no scale. Yes. But even when we look, now look to our fracture mechanics, which we use for industrial application, we usually use this for dimensions in centimeters, or the fracture mechanics samples are usually also larger than typical 50 millimeters or larger. That's our typical size. And even in this region, we have a lot of discussion of sample size effect on, for example, fracture toughness, or in the case of short cracks, the problems that short cracks grow different to long cracks, and so on. So even in this case, and there are for many fracture mechanic scientists thought that fracture mechanic to microsamples is not really applicable. But I will try to show that we have to go this way, and this is really a new area in fracture mechanics. And this, on one side, is important for design of sensors, of micro-electronic devices, and also in order to understand better the fracture behavior of our materials. I am working mainly in this area, but also working together with some industrial partners to use this also for microelectronics. So let's go. So here you can see the main reason why we are doing this research. One is the industrial-driven things are, you have a miniaturization of components, especially in electronics, sensor technique, and also in medicine, but also in many other areas. Here you can see a stand, or if you look to wires where they try to connect nerves and so on. Yes. So these components are extremely small, and they are heavily loaded under fatigue, and so it is very important what happens under fatigue, what happens when they have small defects. Will they grow or not? This is one driving force for this development. The other area for the development of these techniques is that material scientists often want to know, they have complex structures, and they want to know the individual properties. Yes? For example, this was one of the driving forces at the beginning of our researches. It was to know the mechanical properties of bone in different regions. Yes? And or to know the mechanical properties of wood in a certain area, for example, in the wood wall of the cellular material, or if you look to simply steel materials, what happens when you have this, for example, lamellar arrangement of cementite lamella in pearlitic steel. How are the mechanical behavior in the different direction, or what is the interface strength, and so on. So there are a lot of problems in this area. And here you can see typical failures. This is a typical coating failure. In this case, it was a hard coating on a relative, or yes, it was a hard coating on hard metal, so they are two relative brittle material. Here you can see the thin film on a polymer substrate. Then there is a large development in flexible electronics. You simply think on these rollable screens, or but also for for medical application. And here you see a typical failure of a power electronic component. This is a part of a transistor where you have a disconnection of the component, and it is nothing else than the growth of a crack and the failure. And most failures now are not cars, or bridges, or something like. Most failures are failures of micro-electronic devices. Yes. Power, the power supply of these, and all these they are not simply a failure due to the stress. They generate crack, growth crack, and the component fail. And the electronic engineers have not realized this. So they have done a lot of stress-strain calculation, yes, like what mechanical engineers have done nearly more than 200 years ago. Since more than 200 years, the electrical engineers do this also, yes. But they have not introduced structure mechanics, and this is a new area for them. Okay, so here you can see different test techniques, micromechanic test techniques. Here you can see that's one of the first which goes down to the nanometer region. It was nano-indented, so where you simply make hardness measurements, yes, or friction measurements. There are different types of test techniques in this area. But you can go down to indentation depths of really few nanometers, yes, and really get mechanical response. Because the difference to classical hardness test is that it's really instrumented. Yes, you measure the amount of indentation and measure also the force which you need. And from the indentation, from the force and the depth of indentation, you can directly calculate the hardness from simple geometrical relations. Then here you see another very popular, now popular test technique, which was introduced about 15, 18 years ago, the so-called pillar testing, where you simply machine such small pillars and then you make a compression test. Or case of bending, this have we introduced for semiconductors. It was introduced somewhat earlier because with etching technique it was easier to produce it, but then for metallic materials we have introduced this in the beginning of 2000. And also fracture mechanic tests on this scale. So these are typically few microns, yes. These are 3 microns, these are also 3 microns, 2 micron thick. This was a fracture mechanic test on these dimensions. Or here you can see a tension sample, yes. Also 2 microns, or but you will see it on, I think, on the foils which you get. I think the resolution isn't sufficient here. Or here, and these are the smallest tension samples, really tension sample where you get stress strain curves, yes. And the size of them is 200 nanometer, yes. You can really look what happens in the interior of the sample. Okay, in order to get the feeling for those which are not so familiar with these small dimensions, yes. I have plot here, this is a human hair, yes. The human hair has the diameter of about between 50 and 80 micrometers, so somewhat smaller than 1/10 of a millimeter. Yes. And this was the micro tension samples, yes, which are tested typically in a scanning electron microscope, and this would be the real 200 nanometer thick sample in relation to the human hair. That's really tiny things. But in your electronic devices you have a lot of these. Yes. They are even smaller. And you have to predict the mechanical properties of them and the failure properties of the different structural elements on your device. Or functional elements of your device. Okay, So you would say, okay, that's really tiny. Yes, it is hard to look to a hair. And the question is how we far did we have to go? Okay. How we perform such experiments? Okay, we have to do this always in the scanning electron microscope or transmission electron. They're very fine in the transmission electron microscope. What you have seen is we have this tiny sample. We arrange this in the scanning electron microscope. Then you bring, for example, this gripper into the focus of the system. Then you take out the sample out of focus, go above, and then you move the sample below as long until the sample is again in focus. And then you can perform the detection. Okay, now what are the ways to produce these samples? The most used tool, especially for metallic material, ceramic material, are these focused ion beam systems. In most cases now, since this focused ion beam workstation was introduced in the 1990s, originally I think the semiconductor industry have it developed. They always call it for inspection, but in reality, they have buy the instruments for the inspection of the other companies' product to look how they made the devices and how they could realize really such small devices and so on. But then they also use now this really for repair of prototype and so on. So what is this is now a typical system which in this form they're about 20 years old. You have always electron microscope, really high-end electron microscope, typical field emission microscope, so that you have really a resolution of 1 to 2 nanometer. And then you have here an ion microscope, typically usually the so-called gallium, they have a gallium source where there is simply a droplet of gallium and they apply a voltage on the droplet and then they form a needle like the droplet. And from the tip of this needle you get ionization of the gallium and then you simply accelerate and use it. You can use it for imaging, you can use it for removal material, and sometimes you can also use it for deposition. If you use it for deposition, then you introduce a gas, typical, for example, tungsten, chlor-tungsten, or platinum chlor gas mixture, which you very localized deposit or flow over the sample surface, and then you crack this, and then you can deposit, for example, tungsten, platinum, or other elements on the sample. But we use it in micromechanics usually only for removing of materials. This is the gallium is in a gallium FIP has approximately a resolution similar to a standard scanning electron microscope. So with approximately this precision, you can machine also samples. The xenon is a different type of source, but much higher current and you can remove much more material, but the accuracy is not as high. Yes. Or what is now? What is? Okay. Another technique which we have recently developed in our institute, and I think this will come in the future, is this femtosecond laser ablation. This is a new technique where one can, this is again, I apologize, these are about, I think 1 millimeter, no, not one, I think 1 millimeter. So they're medium-sized samples in a tungsten foil. So you would say, okay, that's our at the border where what we can machine with classical machining. So if we would produce, these are all tiny bending samples. If we would use the FIP with this, one would work about 1 year. Yes. With a femtosecond laser, it was half an hour. Yes. So you see the enormous difference in time with this system. It is not as accurate, and you cannot produce very fine notches because you are always limited with the focusing of the laser. Yes. The reason why we use femtosecond laser is very simple. In this case, the removal of material is different to classical laser machining. So classical laser machining melts the material and it evaporates. Yes, if you use, for example, a nanosecond laser, and with a nanosecond laser, you can really buy such a system, which is also connected to a FIP. It is here in the pre-chamber, this femtosecond laser. Then we can really move. We can machine the sample in this pre-chamber, go to the SEM, and can further refine the cutting with the FIP. You can buy a nanosecond laser system, but with this nanosecond laser you have the typical evaporation of the material. You have an enormous heat impact. But with the femtosecond laser, the pulse is so short, it's only one wavelength or two wavelengths, yes, in length. And what you do is you get the ionization of the near surface atoms, and these ionized atoms flow away, and you have nearly no heat impact into the material. And it is also important that you can remove any kind of material. Yes, you can also remove from transparent material. Yes, in principle, it is the same technique what the eye doctors use for cutting of or removing of the iris and so on. Okay, so here you can see a typical FIP prepared, one of our first fracture mechanics sample which we have prepared. This is now here 10 microns. We need about half a day for this. Yes, it's quite time consuming. Yes, I will now try to show how we can prepare such a sample in a very simple way. So one prepare a sample with an edge, and then one look along the edge on which area I want to have my for example painting sample, but the same can we do with the tension sample. Okay, then I remove it first in order to get all the machining problems away from polishing or preparing the edge. Then one remove the material behind, and then one turn the sample, remove this type of materials, and then one cut this. And finally we have a simple like this sample. This was a special sample which will come at the end tomorrow for residual stress measurements in this thin film. You see that this beam is bent, which is a consequence of the Another simple, which is somewhat faster, is when we prepare samples from needles, needle-like pre-products, where we use etching techniques. And then one, especially if we look then to single crystal behavior, then we use this needle technique, because in this case it is not necessary to take the sample at a really well-defined position. In case if we do this in a microstructure and want to measure, for example, the interface toughness, then it is required to prepare the sample at a well-defined position. But if we do it in a single crystal, we can start with a needle, then remove the material on this tooth side, rotate the sample by 90 degrees, and then you have the final shape of your tension sample. Another simple technique which we often use, especially for mass production, is you have a very tiny stainless steel plate, typical 10, you can buy it with dimensions from 8 to 20 microns or even larger. Then when we place this above the sample, then you remove the material with a powerful unisized argon beam. Then you have here, these are now millimeter in length, and the thickness is, you see, 4 microns. And then you have a wall with 4 microns, and then you can simply machine what you want, yes, in this wall. And again, you can tell bending, fracture toughness, fractured experiment, tension experiment, fracture experiment, tension experiment. Then you can perform. So now, how you test it? Usually, especially when you go to the nanometer dimensions, you have to do this always in the transmission electron microscope. When you have samples in the micron dimension, you usually do it in a scanning electron microscope, sometimes only below an optical microscope, within the optical microscope. Especially when you want to look to environmental effects, then you go to optical microscope, but sometimes there exists also environment scanning electron microscope, but it works at somewhat lower pressure than so with about few millipascal pressure. Okay. This is one of the devices, what we use, which is originally designed for fiber testing, or in the most cases one uses nano indenters, type of micro or nano indenter instrument which can measure the load and the displacement, which are originally designed for this nano indentation experiment, and one uses now also for these micro-mechanical devices. Here you see one, this was our first device which we have used for tension and compression devices. So this is a piezo-driven system, nano indenter. You have here this gripper, and then you come with the sample with the procedure what I have explained before. We go to the sample, go above, bring the gripper from the nano indenter in the focus plane, then we take our sample, go out of focus, move above, and go above the sample, the gripper, go with the sample into the focus plane, and then we can perform our tension experiment. Okay, so much to simple the testing procedures and how we can do, we can make the samples and how we can perform the mechanical experiments on these length scales. But the course here, we're not focused to the mechanical experiment, it is more to fracture mechanics. Yes. And at first, let me start with a very basic thing related to the length scales, which are important, which we have always taken into account. Sometimes we have also taken into account these in macro experiments. Yes, it's not only limited to micro experiment, but in micro experiment is really evident, and only very seldom that we can forget them. Yes, that's and therefore I will say some basic things about the important length scale, and then I will talk about the important things which we have to take into account when we think about the scaling effect, the effect of scaling on the fracture resistance. Before we discuss this, we have at first to discuss or to understand what is the effect of scaling on plasticity. Yes. Because when plasticity evolves, this plasticity is also affected by the scale, especially when we go down to the micro dimensions. And then in the second part, we go then to the fracture resistance. In order to do this in a really some way to understand what is the impact of the scaling effect on fracture, it is very helpful to look what are the effect of this scaling in ideal brittle material, in semi-brittle material, and in ductile material. Okay? And then I will discuss during this course only the effect of this mechanism on toughness and fatigue crack propagation, not on creep. Is also important, especially in electronic devices, power devices. So they get heat pulses up to 200-300, the copper layers of up to 200-300 degrees centigrade, and copper creeps, also aluminum creeps at this temperature. So it is really a creep fatigue problem in many of these cases. But in my talk, I will only talk about toughness and fatigue crack propagation. But in principle, all what we discuss during this course can be also transferred to these creep and or environment-assisted cracks and so on. Then I will, during the story, I will also look to some case study, and then at the end, I will also, I hope that we can become so far, talk a bit about thin film problems, which is an area for itself, yes, because it is a bit more complex, because we have always the problem that we have different type of materials, we have a mismatch between the different materials, we have different elastic properties, we have different plastic properties, we have different fracture resistance, we have interfaces, and interfaces have again its properties. They have again fracture resistance, fatigue resistance, and so on. So, and this makes it a bit more complex, but I will hope it works. I don't know why. Not here. Okay. So you have heard yesterday think you will have heard it, that we have in principle two ways to go to fracture mechanics, or in every textbook you see this, yes. You have one way, it is an energetic approach. This was originally introduced by Griffith, and then also Irwin have used this to transfer this idea to engineers, yes, this energy approach. But in principle, he has also developed this stress-strain approach. And I will mainly follow this stress-strain approach. The reason is quite simple, because in this stress-strain approach it is so easy to see the important length scale, which we have to take into account when we look to the fracture of microsamples. Okay? So I think that's well known for persons which work in fracture mechanics. These are the stresses. These are the tension stresses of a crack loaded in tension, so it was one loading. And what happens at very small loads in a linear elastic material, and also even in a linear elastic elastoplastic material, at very small load you will always have this type of behavior. You have near the crack tip, you have the near crack tip field, which has the square root relation, the square root decrease of the stress as a function of the distance, and then you have the far field stress. Okay. When your material is is ductile, and you load it further, then it will start to the plastic deformation. You will form a plastic zone. This is for a hardening material, non-hardening material. The stress would be constant in the non-hardening material. In here within the plastic zone. If you further increase the external load, the plastic zone will increase in size. Yes. And as long as the plastic zone is embedded in this K-dominated area, we call this small-scale yielding. And we can use the stress intensity to describe all properties of a material. Because at a certain stress intensity, we will always have the same stress field in front of the crack tip. That's the basic idea, yes, for small-scale yielding. If the ductility of the material is sufficient high, yes, we can further load up our material. And if the applied stress becomes near the yield stress of the material, we come to the full scale and large scale yielding properties of the behavior. And then in the near crack tip field, we have the so-called HRR field. Also here, in reality, we have also here in the near area this HRR field. In reality, we have here a certain transition. I will not go into detail, but for simplicity, I simply draw this in this way. Okay. Yeah.
For linear elastic, or ideal linear elasticity, won't the curve go to infinity at crack tip?
Yes. But the problem is, it makes no sense to draw this line at distances smaller than 1 atom distance. In continuum, it goes to infinite, yes? At some femtometers or something like, yes? But at these length scales, the stress have no meaning, yes? But from continuum mechanic point of view, it goes to infinity. But definition of a stress for a material has only sense if we talk about distances of our atoms. If we go smaller than it makes no sense to talk about. stresses. So in reality, it goes further here. Yes, which comes later. Then also what really happens in this area in detail. Okay. Good. So it is in principle you would, if you simply look only to the stresses, it would not be clear why our material failures. This is much easier to visualize if you look now to the strains. In the linear elastic case, you see this here, it is clear it is a linear elastic relation. The strains behave exactly as the stresses. So we have again this square root relation here. In the small scale yielding region outside the plastic zone, we have again the same behavior. But when we now come into the plastic zone region, then we see the singularity of the strains become much stronger than in the linear elastic case. Yes. If we would have a non-hardening material, we would have a 1 over the distance singularity. That's much stronger than 1 over the square root relation in the elastic case. Okay, so if you compare this. If we have a non-hardening material, we would have the yield stress here, or we come somewhat later due to the multi-axiality. Only the equivalent stress is equal to the yield stress, not sigma 2. It can be 3 times. That's another story. Okay. So that's important. And so the strains here very near the tip curve are extremely high. And these are the reason why we have this localized crack propagation. Okay? So now we have seen the different regions of the stresses, and in all our consideration we have to look how large are the different areas in relation to the fracture process, in relation to the sample, in relation to the microstructure of our material. Okay, so the first important length scale, I would say the most, or one of the most important, is the so-called K-dominated region. Yes, I call it here the RK. Yes, in this region you can use the near-tip solution, what you usually find in every textbook about fracture mechanics. Okay, this is important. Also, when you look to linear elastic fracture, to pure ideal brittle material, then the next point is the plastic zone size. In the case of, yes, which is embedded in the K-dominated zone, and this is related again, is only related to the K value and the plastic deformation behavior of the material. The same, no, somewhat different is with the HRR field. It has a similarity to the K-dominated area. It is usually somewhat smaller. Yes, one can look how far are these simple description for Bauer law material describe the stress field, but nevertheless it is again related similar to the sample dimension as RK. They are only dependent on the sample dimension. They're not dependent on loading. Okay, and then we have a region where the fracture really takes place. A different type of materials. This has a different size, but it's, I will call it the fracture process zone. Okay, so let us now at first look what is the size of this K-dominated region. So you always see And for this, I have here plotted, or here used, the most condensed form of the real complete solution of the stress field in front of a infinite plate with a through thickness curve. Yes. And here you can see the equations. They are, yes, one may say difficult or not difficult, but I think it is very condensed in this form. So the only thing you have to take into account what are the different radii and what are the different angles. But in principle, this is what you can do even with high school mathematics, yes, to calculate the stresses. Not to derive it, but that to look how are the stresses. So here we have plotted now the maximum shear stress for a mode 1 loading crack of this length, and you see here at far distances the maximum shear stress is about 1/2 of the applied stress. But you see the stress is really complex. Here it is nearly 0, and here we have an increase, but the increase is not as dramatic as one thought at the beginning. Yes. Okay. Now I have looked now to the. This is now the half the crack length. I changed the scale, and you can see here. Oh, that looks very similar what we know from the textbook about this equation here, the near-tip relation. And here, when we really go very near the crack tip, then you can really see, okay, that seems to be that it is really possible to separate our stress in a radius-dependent term and in an angular-dependent term. The position remains always similar to the shape. That's a very indication that such things happen. So these are the well-known equation which you have already heard yesterday. Now, with this square root relation of the stresses, so the important thing if you go along in front of the crack is that you have enormous hydrostatic tension loading. Sigma 1 here in front of the crack is equal to sigma 2. That's at first a bit surprising, but it is so. Yes, really the two stresses you have loading in this direction and the stress in the crack growing direction is exactly the same value. Yes. And that's as the shear stress for the other. And in the thickness direction, you have simply for the plant strain case the 2 times this value, or this value minus 2 times the Poisson ratio. Yes. Okay. Now I have plotted here the stresses sigma 1 again in front of the crack and sigma 2 in front of the crack. And this is the near tip solution. This is the square root, because in a log plot it is a line, yes, with a slope 1/2. It's quite easy. Okay? So, and here you see this is about the crack length, the ratio, the distance divided by the crack length. So this is about the crack length. And, excuse me, this is 1/10 of the crack length. And what you can clearly see that up to about 1/10 of the crack length, the near tip solution is a really good approximation for the stress in the loading direction. The crack for the stress in the crack growing direction, yes, it is a good maybe approximation, but there is a certain deviation. And I would always say, okay, for stress, for distance is larger than about 0.2 times the crack length, the deviation becomes really large for the loading direction and extraordinarily large for the crack growing direction. So these near tip solutions, yes, are valid approximately in this area. Okay? As long as you have the crack is small compared to the other dimensions of the sample. This holds for a relative long time only when the crack becomes is nearly as long or the ligament is small compared to the crack length, then the ligament is the controlling, the ligament size is the controlling value for the size of the K-dominated area. It is approximately, again, about 0.2 of the ligament width. So that's a rough estimation. Yes. Okay. So, the important length scale and the small scale yielding are first, which we know now more accurately, is the K-dominated region. Then important is the plastic zone size, and the small scale yielding, the HRR field is not as important. In some cases, when you look to the special semi-brittle materials, then the stress state is also, the real stress state in the plastic zone is sometimes important to understand it, but important are the plastic zone size and then the fracture process. So when we go to linear elastic fracture mechanics, then we have this K-dominated zone, and in order to be in the small scale yielding, the plastic zone size must be embedded in this K-dominated region. That's the reason. And then we have here in front a certain region where really the fracture takes place. And then we have another parameter which we often will use for as an important length scale, because the fracture process zone, especially ductile material, is always a certain in certain relation to this crack tip opening displacement. But it is the plastic opening displacement. We have to distinguish. In the elastic case, you have a certain elastic opening, and then you have, in addition, when plasticity starts, you have a plastic opening. So in order to understand the different lengths, there is a very nice things in fracture mechanics. Really, if you simply take in a small scale yielding the square of the stress intensity and divide it by a stress to the square, yes, then you always end up with a length scale. And these length scale are really characteristic, yes. If you divide the square of the stress intensity through the applied stress to the square, you get immediately the crack length. Yes. If you divide the square of the stress intensity to the yield stress, you get the plastic zone size for a plastic deformable material. And if you divide the stress intensity factor to the square through the elastic modulus or the shear modulus divided, and the yield stress, which is again stress to the square, yes, two different stresses, then you come to the crack tip opening displacement. Yes? And funny things which may be not so familiar is, if you divide the stress intensity to the square through the yield to the shear stress to the square, you obtain the opening, the elastic opening of the crack, and the first dislocation starts to propagate from the crack. That's really, really nice dyslexia. And I think, I do not know if he was the first, but I found it the first time this in the book of Workman. Yes. I he called it the magic length scales of fracture mechanics for small scale yielding. And it's really impressive because, especially for persons which are new in fracture mechanics, I have studied physics, and when I come to fracture mechanics, I was always, why we have this crazy parameter with megapascal times square root of meter, yes. It's really, this is a driving force for crack. Not so easy, yes, to understand in the beginning. But if we do this, this is really, really clearly visible. In the elastoplastic case, then the difference is, if this is the size of our sample, important that our fracture, the fracture mechanic properties which we determine, if they should be size independent, the requirement is that the HRR field, which develops in front of the crack tip, the Hutchinson-Rice-Rosengreen field, I think you have heard this yesterday, this HRR field should be significantly larger than the fracture process zone. If this is not the case, then you have always to expect that you will have a significant size dependent of what you measure. Okay? In order to look now about the size of the fracture process zone, it is really very helpful to divide our material into different classes. Yes. The first one is the ideal brittle material, and you may know also the last one is the ductile, and then we have somewhat in between. We call it the semi-brittle. Maybe I should make one comment to the definition of brittle and ductile. This terminology is not so clear in the community. For example, civil engineers and sometimes also mechanical engineers have a different definition for brittle failure than material scientists or physicists. Yes. The reason is quite simple. For civil engineers, if a structure fails without macroscopic plastic deformation, we think, okay, this was a brittle failure, yes, because I have not seen any plasticity before, yes. But in reality, it may be really a ductile fracture because it was a small scale yielding problem. The yielding at fracture was very localized, and he could not see this on the macroscopic structure, yes. On the other side, and only when they see that the component really is plastically deformed before it fractured, they call it ductile, yes. But that's not really related to the processes. In the case of the material scientists, have a definition, okay, I have a ductile material, a ductile behavior when the crack, when I have a crack, during loading we have a blunting, and then we have a generation of pores in front of the crack. The pores grow during the further loading, and finally the coalescence, and finally this area coalescence with the crack tip, and I have the crack propagation. This is ductile from material science point of view. And the crack tip opening displacement can be extremely small, yes, in some of these materials. For example, if you look to ultra fine-grained hard metals, which you would say is exceptionally brittle material, yes, but they fracture in such a mode. But the crack tip opening, the cobalt film between the hard tungsten carbide particles is so thin that these films and these pores are only in the size of few nanometers. Yes. But it is a ductile process. That's the real brittle material is the best ideal brittle material is silicon. Yes. There are several semiconductors which are more or less ideal brittle. And in this case, the fracture process zone, that's always in the order of few atom distance, so few nanometers. Yes, typically 1/3 of a nanometer is the distance between our atoms in most of our materials. Very, very easy. I don't know why this happened.
Maybe we need the power source.
Okay. Yes, sir.
To avoid the standby.
Okay. Okay. And so there is easy. The length scale of the fracture process zone, it is always in the order of 1 to 3 nanometers, not more. Yes. And in this case, it is always few times the crack tip opening displacement. So it is, but this crack tip opening displacement can vary in our materials over extreme large values. Yes. In most of our engineering material, if we look to steels or aluminum alloys, titanium alloys, it is in the order of 20 to 100 microns. Yes, 100 microns is usually relative ductile or tough metals. Only in pure metals or austenitic steels you can reach 500 microns. So that's the semi-brittle material. The fracture process zone can be exceptionally large. Yes, it can be very low. If we look to nano composites, it can be quite low, but it can be exceptionally large. The most well-known fracture process zone large one is concrete. Yes, in concrete you can have fracture process zone in the order of meters, and even in meter-sized samples, it is always questionable: are these not size? Are the determined fracture parameter not size dependent? Simply due to the reason that our fracture process zone is larger than our K-dominated region or our HRR-dominated region. Yes. So even in really large samples, we have this problem of sometimes of size dependence, even in meter-sized samples. I will show you here one example of a material. Unfortunately, you cannot see this. Should be a fine lamellar microstructure. Its colony size, well, this is, I think, 50 microns, which is used nowadays as a high temperature material in airplane turbines, especially in the temperature region below 700 degrees C, typically. So the last 4 to 5 rows of plates. And it is used in this so-called lamellar, fully lamellar microstructure. You can have this type of materials in many different, like steels. It is really very complex material. You can generate enormous different kind of microstructures. But for this high temperature application, you always have this fully lamellar microstructure, which has a very good creep resistance. And the size of these are a few microns. And I will now try to show what happens during fracture of these, if you have a crack here inside, and how the crack propagates through such a microstructure. And what we have plotted here is the stress intensity factor and the crack extension. And this is the fracture surface, yes, of a fractured sample. This was the notch. Here, very tiny, small area is the pre-crack, okay? And we have measured the crack extension during the loading in situ in a scanning electron microscope. And here it was the notch somewhere. And now we have loaded the sample, yes? And if the load is transferred to a stress intensity factor, so and first, you see even during this very first loading, from here to here, you see the crack is extended over this region. This is 2 microns, yeah? No, this is 1 micron, okay? About 1 micron grown over this distance, relative brittle. Then, in the next step, you see that it's only blunted this area. Excuse me. From here to here. Now that's one further. From here to here, it is only a bit blunted because it opened. These are now 10 microns, okay? And you see a certain amount, even in this, yes, semi-brittle material, you have plastic deformation. Now we have further loaded, the crack is grown over the short distance, and it seems that the crack develops here in front of the crack. Then if we further load, this was the crack position before. We have this cracking, and here this remaining crack. And then if we load here, these colony fracture, this is exactly this colony here, okay, which fracture, okay. And then, if we load further, this was the crack before, okay. The scale has changed here from, if we have here before, these are, unfortunately, not visible for me, but you can clearly see this was the crack before. Now, a crack developed here in front of the crack. And this is in principle surprising. Many yes, fracture mechanic persons often discuss, yes, there is a crack generation in front of the crack, yes. But that's not true. The stresses here, if we load this crack and the stresses here are very low, it is unexplainable how a crack could generate here. What really happened is, if we look here to this region, the crack tunnels here in the interior, and here is a, unfortunately it is not so clearly visible, but here is a really nice lamellar area, and this lamellar area fracture, and only this bridge remains. Okay? So the fracture process zone is here in the order of a few hundred microns. Yes, we see here from, or nearly 1 millimeter. Yes, half a millimeter. Yes. Where you have, if you load further, then you have this fracturing of the bridge, and finally you have the fracture. The similar behavior a long time before was seen, for example, and this is the case in many of stable grown cracks of steels in the low temperature region. Yes. Here again, this is a pure iron. It was not published. It was one of my first diploma students who worked in this. And you can see this is a crack in a DCP sample, and the crack is grown here. Some of the grains are fractured, but in reality they form into a network, and it remains a kind of bridging zone. And this can be really large, yes, in the order of several hundred microns. So the size of the fracture process zone in semi-brittle material can be extraordinarily large. So in such material you will never determine the size-independent fracture toughness on a microscale. What you can measure are intrinsic properties here, but you cannot measure, or you can measure fracture resistance, but it will always be size-dependent. Okay. Okay. So in order to have in our macros, if we come from the mechanical engineering area, we usually work with metals, and most of our metals have grain sizes in the order of 10 to 100 microns. Yes, and in most of these cases, the microstructural dimensions are small compared to the size of the K-dominated area of our macro fracture mechanic samples. And they are also small compared to the plastic zone size. And therefore, get really a single value material property value. In case of, or especially of ductile material, in case of semi-brittle, it is not always the case. And this is usually now not the case when we go to micro dimension, with exception if you have really grain sizes or composite sizes in the nanometer region. Then the microstructure is again small compared to micro dimension. So if we now look to the fracture processes, especially in the if our sample size come into the micron region, I have to take into account these length scales of fracture mechanic, and I have to take into account in many cases also our microstructural dimension, because then our structure of our material becomes important. It's not, we cannot homogenize our material. And here, this is a typical, for example, typical grain size of a deformed aluminum alloy. Yes, typical microns, say 100 microns or larger. But on the other side, you see there exist also materials, ultra fine grain, nickel, where you have here grain size in about a few hundred nanometers. So if you have a sample with 10 micron size, then you could be homogenize the properties of this material. But if your sample is only 1 micron, then you have to take into account the real microstructure of this material. It will depend where you have the crack in the microstructure. And when you go further, these are about 0.5 microns. This is a transmission electron microscope, and these locations, I will come somewhat later to this. These are the carrier of the plasticity. They form, you can see that small deformation, you can see this simply as line in the microstructure. These are typical precipitation. I think it is an aluminum alloy. And so you have, if you have now sample dimensions which are in the 10 micron, then you have not to take into account these local microstructure. But if you make samples of 100 nanometer, you have to take into account. This is a heavy deformed metals where the dislocations are extremely dense packed. These are 500 nanometer or 500 nanometer, where you have millions of dislocations. And this is here one dislocation in a crystal, where you see here, this is a perfect lattice, a high resolution image, and here you see one defect. Yes. And if you look to a metal, always in this with this resolution, you will see always a nearly perfect crystal. Sometimes you will see such a defect. That's this was one of the really big questions 100 years ago. They have performed X-ray analysis they have developed the diffraction technique and have seen, okay, if we deform our material, it always remains crystalline. What happens there, yes? And the only thing what happens is that this defect moves. And if you look very carefully, you always see these nearly perfect crystals. And so if you make a modeling of the material and you say, okay, maybe your mesh size is not sufficient, it makes no sense to make your mesh size finer and finer, because if you make your mesh size with 1 nanometer, it is senseless, because the mechanical properties which you use will not reflect what happens at this scale. Okay, let us at first start with ideal brittle or nearly ideal brittle materials, because some of the nearly ideal brittle materials, like a window glass, can also be considered, but it is not really ideal brittle. It is a bit larger than the Griffith toughness, but you can treat it, and this fracture process zone is not significantly larger. In this case, it is quite simple. You can also, because the surface and the non-reversible process which may happen in, for example, window glass, they are also related to areas similar where the fracture process zones takes place. So, and this is what we called before about 1 nanometer or 2 nanometers. Yes, that's not large. 2 nanometers is the maximum size where the fracture takes place, where the non-linearity of our deboning process really are important. And also the non-linear, the effects which may cause a deviation from the ideal brittle behavior are in many cases are related to this area, for example in window glass. And in this gamma the surface energy is more or less independent of the size. And therefore, the fracture toughness is in principle independent. You can also go even to nanometer size. Example, it ends when you go to maybe the size of few nanometers. Then it becomes again a domestic problem. But as long as your sample size is larger than 2 nanometers, then you are out of the range. This is very seldom that you can do this, because in most cases, for example in metals, you form an oxide layer which has approximately the size of this. It's only gold. Gold you can really make wires of nearly one single atom of gold, but this behaves then somewhat different. But that's a special story for physicists. Okay, but nevertheless, testing of because it is really often the case that one tries to understand this ideal brittle behavior, especially fractured interfaces, but also the semiconductor industry have very often this problem of nearly ideal brittle behavior of materials, and they do not know how the toughness change when they change, for example, the chemical composition of their of the coating material and so on. And so they have nearly ideal brittle, and so they want to measure it, and not only with trial and error. Usually in the nearly whole semiconductor industry, they work with trial and error, like the Smiths in the medieval time. Yes. But they want really to understand this, and therefore they use now this technique also to quantify it. But it is not always simple, even if it is size independent. Yes. And what are the reasons that one of the problems is the notch root radius to really produce a crack, atomistical sharp crack, and the other one is to locate the crack, the notch or the crack at the plane with the lowest fracture toughness. That's the two. But at first, let me say what is the shortest crack length where the simple fracture mechanic works. So what happens? You see again here our atomistic crack, and this here are the stress fields which we discussed before as a function of the distance of the crack at the same stress and density factor. This is the sigma 2 value. Yes. So in the loading direction, and here for different. This is a 10 millimeter long crack. This is a 500 nanometer long crack, and this is a 10 nanometer long crack, and all are loaded with the same stress and density factor. So if it's loaded with the same stress and density factor, it means nothing else that our near-tipped field is exactly the same. Yes. Only the far field stress is different. Yes. And so what you here now clearly see, okay, this K-dominated zone, the long crack is really large, yes. It's nearly 1 millimeter. In this 500 nanometer long crack, it is 50, at least, yes, about 50 nanometers. But in the 10 nanometer long crack, it is only about 1 or 2 nanometers, yes. So it is in the order of the fracture process zone. And therefore, and if we now look to the fracture stress divided by the theoretical stress of a material, you always have a theoretical strength where you can separate the atomic bonds, yes, by shear or by decohesion. This is the theoretical strength by decohesion. If you have a defect, your stress cannot be larger than the theoretical strength. Yes, that's clear. Okay, and when your defect size is very large, the fracture toughness describes the strength of your material. It is simply the square root 1 over the square root of the crack length in this area. And when the crack length, this is the Burgers vector, you can say the lattice spacing, yes, which is typically 2 to 3 angstrom or 0.2 nanometer. So when the crack lengths come in the order of about 20 nanometers, then we get the deviation from this simple fracture mechanic estimation. And then we have a transition to the long crack behavior. And here, Wertmann has used to describe this transition with fracture mechanic tools, where he used the so-called Barnblatt model, or it is a cohesive zone model, which is very often used now for complete other things, but it was originally developed for the description of ideal brittle material from Barnblatt on the base of on a stress-based concept in the beginning of the 60s. Wertmann has now used the same concept simply to look what happens when we go here to nearly nanometer cracks. And in principle, it works. The only difference is one has to use one has to take into account the nonlinearity in the cohesive zone. Okay, so that we can really use it to really very, very small crack lengths. In standard micromechanic experiments and even nanomechanic experiments, they do not really have an impact, this very short crack length, because crack lengths in the order of, you will see, of 2 nanometers are nearly impossible to realize with machining technique. But one should, in the discussion of the properties of material, is often important, because, for example, aluminum forms an oxide layer of typically, yes, 2-3 nanometer thickness. And the question is always, when this layer fracture, behave this crack as a real crack or not? So, and here we are really in this area with this type of cracks. But this is out of the range of standard fracture mechanics. But it is important when one discuss this phenomenon. One should know this relation, that when the crack is so short, then you can assume also the theoretical strength. It is not really dangerous if you have a crack in aluminum in the oxide layer. Okay, the next point is focused ion beam workstation really allows machining with nanometer precision, exceptional. But if you machine a notch, the notch radius is typically, if you use very small current, it is always larger than 5 nanometers. Yes? But 5 nanometers are large. Yes? This is a atomical sharp crack. Yes? And these are 5 nanometer crack. Yeah? So it is not really atomistically sharp. And that's often when we measure then the toughness of these nearly idle or ideal brittle material, then it's always the discussion: is this really the toughness? Can it not lower if we would have really an ideal brittle, atomistic sharp crack? One of the ways which we usually try to do is to introduce not a straight crack front, to introduce irregularities along the crack front. So, for example, one machine the notch, and then really good resolution. And here we have a small bridge, and then we load up the crack, or we load like the chevron. This in principle the classical chevron technique what we use, but it's difficult to produce a really well-defined chevron notch with a fit. Especially you have a chevron notch with a very sharp notch root radius, because the stress intensity, which usually at a constant load increases with increasing crack length, but in this chevron notch, it decreases because the length of the crack increases. Yes. Or the length, the width of the crack increases by appropriate design of the sample, the stress intensity. And the advantage of this chevron notch is that it is not really necessary to measure the crack length. The only thing you have to measure is the load. That's because if you know at this load you will have critical crack propagation, yes, at this length and at this load, and then you can simply calculate the stress intensity. But we don't, in micromechanics, one usually do not use the chevron notch because it is a bit difficult to really fabricate it. But one introduce some irregularities, and then the crack starts at these irregularities, and then one have a pre-crack along this notch, and they can then travel through the notch. Here you can see some of the experiments also for semiconductor, in the semiconductor area, where we uses here different, or where we have measured the strength and toughness of different type of isolation material, silicon oxide with a certain amount of nitrogen and hydrogen. And what you see is the strength of these materials is always very near to the theoretical strength of this material. They have an elastic modulus in the order of 80 to 100 gigapascal, and the strength is about in the order of 6 to 10 gigapascal, which is about 1/10, and that's always the rule of thumb, that the theoretical strength is about 1/10 of the elastic modulus. Or in other words, if you have no defect, you have no dislocation, and you load up a sample, you the maximum, the strength which you can obtain is the theoretical strength, and this is or the strain which you can apply is about 10%. 10%, the distance, change the distance between the atoms. And that's not so different in different types of materials. And then we also measured the fracture toughness. And in reality, what you see is the fracture toughness of this semi-brittle material, in this case, scales relatively good with the elastic modulus, which is not so surprising, because one would assume, okay, this different type of doping, they affect the elastic properties, but it will not significantly affect the surface energy. And then the relation between surface energy and fracture toughness, they are related to elastic modulus. All these things, what we have discussed here, is also a problem in semi-brittle materials. Yes. If we have a problem in semi-brittle material, we always, in most cases, we want to study individual processes in the semi-brittle. But even when we try to measure, for example, the interface toughness, the problem is here at first the notch root radius, and the second one is to fabricate a notch which is really perfectly located at the interface. If it is not perfectly located at the interface, it is not surprising that you measure completely different story. And even if the interface is only 20 nanometer away, but 20 nanometer is really a huge distance, yes, for atomical sharp cracks. Maybe here. This was a trick where we have measured the interface between silicon oxide and copper, where we have simply, you see here this bending beam of copper, and here is the silicon, and we load up the sample here. It will fracture. Unfortunately, this video will not work here in this version. But What? Oh, it doesn't work. Excuse me. I don't know why it doesn't work. Transfer. Okay, then we start again.
Start?
Yes.
To
Yes. Okay. So you can see here a typical experiment. So it is, you have seen before this displacement curve. And here, yes, because it is fast running, the scan was very high. But now you see the crack is generated, and then you can look to the growth of the crack. And from the growth of the crack at the interface, you can then really determine the interface toughness of these materials. So that's one of the other things that work. Okay. Okay. Another problem which we recently also studied, this is a semi-brittle material. When we will make a break, and I think we yes, and we'll go through this part, few parts, and then we make a break. This is we are looking for the fracture behavior of tungsten foils and wires. The reason is tungsten foils and wires are interesting a material for high temperature application, for fusion application, but also for many other applications. But tungsten has one drawback. Tungsten is as a polycrystalline material, really brittle at room temperature. Yes. And in order to overcome this, we have looked if we can overcome this problem with a microstructure, a very lamellar or needle-like microstructure with grains of few nanometer thickness. And really, at room temperature, the toughness of this material is exceptionally high. It's in the order of 80 megapascal per square root of meter. And here, we could not really measure it with linear elastic fracture mechanic techniques of these wires. You clearly can see this is really neck. Yes. But what you see, it is really a fibrous crack with large plastic deformation, and the fracture toughness is again in the order of 100 megapascal per square root of meter, like a steel. Yes, this is for persons which work with tungsten. It is fantastic. Yes. But what you see is we have always this delamination. One of the questions we try to solve is what is the fracture toughness of these for this delamination of the grains. And we have again for the foils and the wires. And what we have done is, you see these small samples we have cut out from the wires and also from the foils. So it's nearly DCP samples, not really. But we have a certain mixed mode loading. Nevertheless, you see we have loaded this with a special fiber loading device and measured the propagation of the crack. What you see here is the change of the fracture toughness as a function of the crack length. So it is also this type of loading is a semi-brittle. But this is nearly ideal. See this at 2 megapascal per square root. That's exceptionally low for fracture toughness. That's the reason why we get this delamination and the good fracture toughness in the other loading direction. And here you see it is significantly lower than in the case of wires. And the reason, becomes quite evident if we look in the wires. We had these needle-like grains with about 200 nanometer, 1 to 200 nanometer needle diameter, and here we have this pancake structure with about 1 to 200 nanometer thickness of the pancake. And when you look here, now this is the wire, the foil which is splitted, and here the crack was nearly laid exactly in the plane of the lowest fracture toughness. But in this case, since you have the needles with 200 nanometers, yes, which has this 200 nanometers and we have a notch, and the notch is in most cases not at the weakest point along the crack. And therefore, we start significantly higher with the equation, and also then the bridging is more pronounced in these wires. Yes. And this shows clearly how important it is, if you really want to measure the intrinsic properties, to really look to place the crack at the position where you have the lowest toughness, where you expect the lowest toughness. Another example is here, where we, for the brittle fracture of tungsten, of single crystal tungsten, it is we have looked in microsample what is the effect of the deviation from the ideal brittle crack plane. So we again machined that microsample and deviate the notch. Oh, that's wrong. Okay, tungsten. I want to say only a few words tungsten, because it is very helpful material to explain why fracture mechanics is important. These are the stress strain curve of single crystalline tungsten at different temperatures. Okay, so you can see the single crystal at room temperature. We are here, or this is we are here. Here we are at room temperature. It's exceptional ductile. Even at liquid nitrogen, this is here in between 4 and 5. The ductility is even better at liquid nitrogen of the single crystal, enormously ductile. Yes. Only when we go to the temperature of 20, in the order of 20 kelvins, which is the temperature of liquid nitrogen, then you see really a significant reduction in the ductility. When you now compare the fracture toughness of the same material, and you look to the fracture toughness here at liquid nitrogen, it is 3 megapascal to the square root of meter. This is nearly Griffiths toughness. It behaves nearly ideal brittle. And even at room temperature, it has only 6 megapascal times square root of meter. It's like a ceramic. Yes. And we come to a ductile to brittle transition, we have to go to 300 to 400 degrees centigrade. So this clearly illustrates the enormous difference between ductility in a tension experiment and in a fracture toughness experiment. And this is so that mechanical engineers, some of the groups, they don't like fracture. I do not know why, but then if one show him this story, then he see why it is important. So we have already, I've mentioned that we have made samples with different notch geometries, and you see the interesting thing on the micro dimension, the behavior is again relative ductile. It is not really ductile. It is a semi-brittle fracture process, but the semi-brittle fracture process is extremely dependent on the angle from the deviation of the ideal angle. So the fracture toughness becomes exceptional dependent on if we are at the lowest crack plane or on the crack plane with the lowest fracture resistance or not. And this is the case for semi-brittle as well as for ideal brittle. Okay, then we make here a break, And then we come to the next point, which we have especially to take into account when we go to semi-material and ductile material. It is that plasticity becomes size dependence, and when the fracture process zone comes in the order of our plasticity dominated atomistic defects. Okay, thanks. We make a break for 10 minutes or so.